Hello, everyone. Welcome back. Today, we want to learn about complex numbers. Our goal are first to understand where complex numbers, what it is, where it comes from, and also understand the difference between real numbers and imaginary numbers. We'll explain each one of those. So first, let's talk about over here on the right, where complex numbers come from, and why we need to understand them. And for most of the times, so for us, basically they come from solutions of quadratic equations. Now, it's not the only place they come from, but for what we're doing, that's where we're going to see them the most. So, for some examples of that, let's say you want to solve. Example number one, you want to solve. Let's say a simple one like x squared equals 2. Okay. Well, as you may know, the easy way to solve that is use the square root property, or basically, which is almost like taking the square root of both sides. The solution to this is x equals plus or minus the square root of -2. I'm sorry, hang on. I should make this back up. It should be a -2. Right, -2. And so we have to find some way to deal with this, okay, the square root of a negative number, okay? Or maybe you have a solution to a quadratic equation, and maybe you're doing the quadratic formula, and say it looks something like this. Maybe it's x equals 2 plus or minus the square root of maybe -8 over 2, something like that. Okay, if you work with the quadratic formula, you often get expressions like this. And so we have to find some way to deal with the negative under the radical sign. So that's where the idea of complex numbers comes from, and imaginary numbers. So what we can do, let's go over to the right. It says we can rewrite, explain I, which is how we deal with complex numbers. So if you have the square root of -1, we can rewrite that as this. I is equal to the square root of -1. Okay. Now, one thing to mention, we're just renaming it. Okay, we're not solving anything, we're not really fixing anything, just making it easier to work with. Okay, so see a square root of -1, we're going to place it with I, and as we'll see, we can actually then convert these to that form. And we'll see that in other videos. Now, also we have a couple properties on this. If you square I, then you get -1. Kind of like you square a square root, you get what's underneath. Okay, then for any radical like these, we can convert these to, we can make it look like this. So square root of negative x, we can rewrite that as I times x. Okay. And it shows, for example, we can write, if you have the square root of -2, like we do here, then I can rewrite that as, it doesn't matter which order this is in, since you're multiplying, just make sure it's clear. If you write as square root of 2 times I, make sure it's clear the I is not under the radical. Or you also see it written as I times the square root of 2. And I kind of reiterate this here. We're not solving, we're just giving square root of -1 a new name. Okay. And this is what's called an imaginary number. And it's different sort of real numbers we're used to all the time. Okay, so let's actually quickly talk about real numbers. So any number multiplied by I is an imaginary number. Let's take a quick look and look at some real numbers and imaginary numbers. Okay, so real numbers we deal with all the time. Okay, so for example, like 2, -1, any fraction like 7/3, rational numbers like pi, okay, anything like that, or even decimals, 1.312, anything like that. Those are all real numbers. Those numbers we deal with all the time. Okay, we make some of these negative. Now, imaginary number is any number multiplied by I, which is multiplied by the square root of -1. So it could look like, 2i, okay? Or negative 1i, let's write as negative I, okay? 7/3 I, pi times I, or negative 1.312 times I. These are all imaginary because they're multiplied by an I, okay? And they're different numbers, and we don't really, in most of the work we do, we're not going to deal with those too much, other than in, once again, in solutions of quadratic equations. Now, the last thing I want to mention is what's called a complex number, and that's the combination of both of these. Now, a complex number, the solutions of quadratic equations usually involve an I and end up looking like this after you simplify them, a plus bi. This is what's called a complex number, okay? So a plus b times I, where it's kind of a combination of both of these, okay? So the a, this is the real, what's called the real part, okay? And actually the b, and only the b, is called the imaginary part. Okay, and many solutions to quadratic equations that involve I will look like this, where you can have a real part and an imaginary part. Okay. Yeah, and also all numbers are complex numbers because every real number can be written this way. Okay, and I'll explain. So let's take a quick look at some complex numbers, some examples. Okay, I'll just say all the numbers above. Okay, all the numbers above in these two tables here, because we can write each one of them in this form as well. Okay, for example, the first one, okay, so we can have 2 plus 0i, okay, that version we had. In this case, our imaginary part is 0, just 2, okay? Or like the fraction we had, so 7/3 plus 0i, okay? And so all the numbers above can be written this way. Or on the other side, we can have like 0 plus 2i, where the real part is 0. Or once again, 0 plus 7/3 I, where the real part is 0. But then we can also have other examples, okay? I'm going to say and others, and this is what we'll often get from quadratic equations, something like 2 minus 3i, okay? Or maybe negative 4 plus I, okay? 2/3 minus 3/5 times I, anything like that, okay? Where you have both a real part and imaginary part. Sometimes we have those. But sometimes we only have just the real part or the imaginary part, or the other part is 0. Okay, but these are all complex numbers. So every number we know is a complex number, because most of the time we deal with the real ones where there's no imaginary part. Okay, last thing I want to look at today, and this is something more of interest, or about the powers of I. Okay, because what we see is a pattern in the powers of I. So first let's take a look at the first one. So I, of course, we know I is the square root of -1. I'm simply say that I is equal to I. Not very interesting. Okay, now one of the properties of this is that I squared equals -1. Okay, now what about I cubed? Well, what we can do is we can use I squared and I cubed, or sorry, I squared and I, also the thing this is I to the first power, to find I cubed. Okay, if you recall, for a rule of exponents, is if you're multiplying exponents, multiplying numbers with the same base, I squared times I to the first. So these have the same base, both I. Then we add the we're multiplying, so we add the exponents. 2 plus 1 is 3. That's the same thing. As we just said, I squared is -1, and -1 times just I, this becomes -I. So I cubed is -I. Okay, now let's take a look at I to the fourth. Now, how can we write that? Well, a couple ways. We can simply do it as, we can do it as I squared times I squared. I'm going to do it in the same way as I cubed times I to the first. We just found that I cubed is negative I. That's times I. And so we're going to have negative I squared. And that's going to be negative times, and I squared is -1. That's going to be +1. Okay. So that's the first 4 powers of I. Now, let's take a look at I to the 5th. Let's repeat this, and we're going to start to see a pattern emerge. So I to the 5th, we can write it in a similar way as I to the 4th times I to the 1st. Now, we just learned that I to the 4th is 1. So 1 times I is just I. So notice that's the same as I to the 1st. I to the 6th, make that a bit better. I to the 6th in some ways, I to the 5th times I to the 1st. Okay, we just learned that I to the 5th is I. Okay, and then I to the 1st is I. So we have I squared, which we know is -1. So hopefully you start to see a pattern here. Okay, I to the 5th is the same as I to the 1st. I to the 6th is the same as I squared. So we might expect that I to the 7th will be the same as I cubed. And as we'll see, it is. I to the 7th, so use the one before. I to the 6th times I to the 1st. So because 6 plus 1 is 7. And so we just learned that I to the 6th is -1. I to the 1st is I, so this is -I, as we expected. Same as I cubed. Then, finally, let's do I to the 8th, and we expect it to be +1. And so let's do I to the 7th times I to the 1st. And we just learned that I to the 7th is the same as -I times I, which is the first, which is I. This is going to be -I squared. And just like we had here, that's going to be negative times a -1, which is going to be a +1. So this repeats. This pattern, as we'll see, repeats. So we can actually use this then to simplify complex numbers we need to. It's kind of interesting, but also we can use it to simplify things. So let's do a quick example of that. Say we want to simplify. All right, so let's say we simplify I. Pick one. Let's say I to the 13th. I'll show you 2 ways we can do this. Now, for a small number like this, it might be easier to just kind of go through the pattern. Okay, I to the 13th, just start counting. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I to the 13th is going to be the same as just I. Okay, just kind of count through the pattern. Now, if you have a really big number, that's not going to be very useful. Okay, so once again, we do this from counting through the pattern. Okay, now let's do another way. I'll say, or let's take a look at our exponent. So remember, the pattern goes to the first 4 powers of I. Okay, now what I think about this is that let's take we're going to divide our exponent 13 by 4. Okay, where are we going to do that? Well, if we do that, then divide it by 4. That's simply going to be should be 4 point, I guess 3.25. Yeah, 3.25. Almost think of it as long division. Okay, so we divide that by 4. That's going to be 4.25. Now, why is that useful? It's 3.25 rather. Sorry about that. Now, how is that helpful? Well, we can do then is we can say that 4 goes into 13 3 times. So 4 times 3, which is 12. And so what I can do is I can use the power, use rules of exponents, so I can write I 13th as I to the 12th times I to the 1st. Okay, now why did I do that? So the reason I do that then is that I have this rule here. So if an exponent is what's called a multiple of 4, excuse me, a multiple of 4, so in other words, 4, 8, 12, 16, and so forth, you can divide it by 4 evenly. Then also let's call the exponent n. Okay, so if the exponent n is a multiple of 4, then I to that n, whatever that n is the same as 1. Okay, because as we saw, I to the 4th was 1. I to the 8th was 1. If you compare the pattern, I to the 12th is also 1. I to the 16th is 1, and so forth. So if your exponent, if you can divide your exponent evenly by 4, then I to that n is just going to be 1. So this becomes I to the 12th is 1. And this implies that I to the 13th is going to be 1 times I to the 1st, which is just I. Okay. So basically the best, if you have a really big number, especially if this has been like, so 13th, it's been I to the 130th, the best thing is divide your exponent by 4. Okay, it's going to give you some whole number plus potentially some decimal. If it divides by 4 evenly, it's going to be 1. If it gives you some decimal, then multiply 4 by the whole number, okay, and then kind of subtract that from what's left. Figure out what your powers have to be to add up to that number, x exponent, and then one of those, then the one that divides by 4 evenly, will be 1. Okay, now that's just something if it comes up, it doesn't happen all that often. So what we learned today in this video is the basics of complex numbers, where they come from, what I is, a few of the properties of I, and then also what complex numbers are and how they're related to real numbers and imaginary numbers. Thank you. Have a good day.